Okay. So screen sharing. And this is on. And then finally, I'm going to turn on my little, I love my pen. Great, my pen. Hold on. Let's see if the pen actually works with um, stylus. So that's the real test. Where's my stylus? I have got it. That's it. Yeah. Ah, excellent. The clown show. All righty, here we go. So let's do this. So what I want to do just for a second is go back into here, and I'm going to go back into the slideshow for a second, and I want to just do a momentary review of these things. So first of all, we're talking about data classification type things. These networks are going to get input data, okay? The input data that we could expect for our network in this lab is basically going to be 4 arguments or something like that, or 2 arguments or something like that. And so you can think of being given some 4 data points that represent, I don't know, like whatever the inputs are, or 3 data points, or 2 data points, or 10 data points. But those are going to be a representation of the input, and you're going to be responsible for coming up with some number of outputs. So what I talked about yesterday in the context of these things was basically just like single output networks, right? So we have these activation functions, right? We went through and there were these different functions and we have these inputs, and these inputs get weighted. They all get weighted, they get biased, and those weights and biases wind up creating some complicated function, right? As they go into here. So the weights and biases create some complicated function, thank you. And we're going to need to create this thing. We're going to need to create this neuron in this lab. You are responsible for creating this guy 100%. And the answer for this guy is going to be a class. I really don't know how else you represent a neuron other than a class. So do you remember Python classes from the last time you did Python? Do you remember doing these things? You did not Python classes. Okay, so this is a good litmus test for me. So this is going to be absolutely like critical that we're using Python classes, so we can kind of, that changes where I'm going with this today. Great, and it's going to be ad-libbing. Wonderful. So bearing with this though, what the idea was that in these neurons, right? So once we have these neurons, they're the fundamental units of these things, and that these neurons are going to be doing some combination of these like functions that wound up getting biased, which is to say shifted, and they wind up getting weighted, which is to say the inputs get scaled to create some really just like complicated function across the input space that maps the output. So if we have our input space that looks like this guy over here, there's some complicated piecewise mapping that's completely nonlinear for these things. And it basically is trying to take this input data and squash it down and remove any sort of trend line to it, right? It's trying to take that input data and squish it right onto that y-axis such that class 1 is above 0 and class 2 is below 0, and class 2 and 3 and 4, whatever, is below 0 over here. Now, one thing that I didn't say yesterday is that what's also common with these things is to have multiple outputs. Oh my gosh, we could have multiple outputs. So the reason you would have multiple outputs is that you might want to have multiple class decisions going on here, right? So I could take these outputs. So if we see these 3 lines going over here, it's also entirely possible. So each of these lines are going to get their own weight to go to here. Each of these lines get their own weights over here. And then we have these effectively 3 outputs to this layer. And so what this is saying is that maybe this is the Virginica output, and this is the Setosa output, and this is the versicolor output. So these are the 3 different types of irises. And when one of these guys goes up, the others are at 0. When this guy is up at 1, these others are at 0. And when this guy is up at 1, these others are at 0. And so what we've effectively accomplished with this is we've created not just one of these complex mappings on the axis. We've actually used these weights to create 3 complex mappings that get squashed to sigmoids. Okay, so inside of these weights, inside of all of these weights and biases, is a generalization that is sufficient to transform 3 messages, or sorry, 3 things, 3 different inputs in 3 different ways. Ask me a question about that. Somebody give me some feedback on this guy. Thoughts and feelings for this. It's okay to say yeah. It's also okay to say, tell me more. Yes.
So for the signal function, like does it need the all the way at like is it applied to that very last neuron or like
So typically the sigmoid is applied to the sigmoid function is an activation function, and that's a function that exists within this so guys, I don't really know what everybody's working on back here. I've got like math, I've got all kinds of stuff. I'm happy to like not do this at all if that's the general consensus that we don't need to do this. Okay. So the sigmoid is happening within here. So the sigmoid, so this is maybe not the best example over here, but the sigmoid is happening at this point inside of here before that data kind of comes out. So typically this neuron is only the last neuron that's going to be given a sigmoid function. In our specification for the autograder, we're going to have like unilateral, everybody's going to be given the exact same activation function. So it's going to be a little bit wonky and weird and not completely consistent with what I'm saying, but the sigmoid is happening inside of here, so to speak. Like in this neuron, this is not maybe the best picture, but this activation function is actually like, he's actually part of like this is the neuron itself. I don't know if that makes sense. Like that's the neuron is the weighted inputs, the biased, the activation function, and then yeah. I don't know if that clarifies that a little bit. Yeah, sure. The activation function is part of every neuron. That is important. Yes, the activation function is part of every neuron. You had a question as well, sir.
So can you go back to the next slide?
Sure. Yep. This guy.
Yeah.
Yep.
So kind of node
using yes. Yes. At every node, we are using the activation function. That is an important thing to keep in mind here. So every node has weighted inputs. Every node has an activation function. Oops, sorry, I didn't mean to do that. And the reason that this is sort of relevant is that if you have all kinds of like mathiness coming into here, like a whole suite of numbers coming into this guy, if this individual, I'm going to erase everything that I have up here. But if you look at this individual neuron right here, right? So I don't love this picture the more I see it. These are just our inputs. They're not. This is a single input, but let's take this neuron right here. I'm going to call this guy A or 1. He's going to get some weighted input and he's going to get some bias that winds up coming out of this. And let's say we get some ReLU function that comes out of this, some linear rectifier, and it winds up being this function that looks like that over here. This function over here, so let me put an axis on here. So he is slightly offset from 0. He's slightly offset from 0, and he has this particular slope. This function over here is going to also be given all of the same inputs, and it's also going to do its activation function. For example, the ReLU activation function, where it's 0 below. It's given a weight and a bias, and let's say that the weight for all of this actually winds up driving it with a negative sloped function. Okay, so this becomes a negative slope function, but we say we also have some bias that makes it really far back on this guy right here. When we are examining these two as they come together over here right now, this guy, you're going to remember, is the sum, right? He is going to be the sum, that's a horrible sum symbol, of the output of this guy and this guy and this and this and this and this. So he's the sum of all of these guys. But effectively, when we're summing these two together, the output is already going to be some weird sort of shifted thing. Plus, so if I take this function and add them together, they're already getting added. Thank you. They're already getting added together in some piecewise way. And then we could imagine that the other weights and biases have contributed to maybe this having other sorts of things. Like maybe it has like additional steepness that it picks up right here. And then it sort of flattens out and then it has some additional. So the transformation is really this strange nonlinear space. I don't know if that vision is helping at all with these things, but each guy gets their own activation function, right? So his own activation function transforms this data from just being like data points into some weird mapping of input. So my input, if my input is like 0, it comes out as 0. If my input, if my input is -4, I perhaps get this value. If it's -2, whatever, yes.
Are there like different types of like nodes? Because I feel like the first nodes were taken like for like the iris example, it would take like the sequel and the pedal like
Yes.
but then they would output like a score, right, based off how that is. And then
Right.
that's getting fed in. How does that get fed into like the next set of nodes?
Right. So the output, so these scores, so to speak. So I kind of don't love the way that this thing is looking at this right now. I'm gonna just make an entirely new thing right here. And oops, sorry, I'm gonna make you larger. And I'm going to go one step further. So if I have input, if I have these inputs coming in over here, the sort of simple reality is that if I have 2 input nodes over here and 3 I1, I2, I3, I4, all of these inputs are being fed. All of these inputs get fed into these guys. So I don't, oh, you can't really see this. But let's do this guy. Make this weighted a little bit heavier. So all of the inputs get fed to each of these guys. So you can sort of see the difference between that 1-to-1 thing that was going on over there. Like I like this description a little bit, or this visualization a little bit better. So the thing that's coming out of here is some weighted sum. It's simply going to be some. If I have 2, it might just be some function that looks like this, right? So repeat your question, and now that I have my visualization.
Yeah, so like those nodes let out like the weighted sum, right? But
how yes.
Does that weighted sum go into
yeah, so this weighted sum, let's say this weighted sum looks like this guy, and this weighted sum looks like, ooh, he looks like this guy. These weighted sums are going to be then fed in. So I'm showing this as like a function, but really what this is going to be a numerical value, right? So this might be the number 0, or it might be the number 12 or something like that. Like there's actually some computation that's going on here. And so an input of an input where the sum of all of these guys winds up being like 10 gets mapped to 0 over here means that I might have like a 0 output and a 1.2 output coming out of this guy. So I'm getting individual numbers that come out of here. And so what I'm trying to show with these graphs is I guess, a 2D mapping of maybe just a single variable, right? Or like the single sum of all of these, or whatever. It's kind of arbitrary on the input. But each of the sums, whatever that computation is, as passed through that ReLU function, which is to say, as passed through the ramp function or the sigmoid function, then will get passed to each of these individual networks. So I need to look at this guy. So they get passed to this guy. I don't think I'm answering your question though. Say your question in one more time.
Yeah, I guess I don't understand like the purpose of the second set of nodes. Like, what do those do with like the scores from the previous set?
Okay, so the purpose of the second sets of is to apply additional nonlinear transformations. So by combining these layers, by combining these guys, and by combining these output functions, what you can do is create complex mappings. That's the long and the short of it. If you think of this as mapping just to a linear space, because the output of this over here is going to be the combination of one linear space and another linear space, what we wind up getting is, or sorry, as soon as this becomes a piecewise function, it becomes a nonlinear space. This went from a linear input to a nonlinear output. And so what we wind up getting over here in each of these nodes is an order of magnitude more complicated nonlinear output. So this over here is an order of magnitude more complicated of a nonlinear output than this guy was over here. So this one started off as linear, then we've got nonlinear. These two are linear. I've got a nonlinear output over here. I've got a nonlinear output. I've got a nonlinear output. I've got a nonlinear output. So as we go through each of these things, the space becomes like additionally more and more nonlinear. And the point of the nonlinearity is that through these nonlinearities, we can begin to sort of shift and adjust the inputs each. Rohan.
So for the first set nodes,
Yes.
like choose weights based on what you think is most important. Right?
So we actually choose random weights. We're going to let the network figure this thing out. So what we're saying over here is that like this thing, the weights of all of these guys just get they're started completely, they're initialized with completely random variables. And what we're going to have the network do is adjust. I'm going to say, okay, hey, here is my inputs. Here's the target, right? The target of this final output is either a 0 or it's a 1. And based upon the final value that gets put out of this in the end, as sent through the sigmoid that maps it to a 0 and 1, based upon the actual value that comes through the output of this guy, I'm going to look at the difference of that. And if this value is not the expected value, I'm going to go through and tweak everything by just a tiny little bit, tiny little bit, tiny little bit, tiny little bit, tiny little bit. So everybody gets a tiny little bit of adjustment. And I'm going to analyze the direction that those adjustments go in a way of hoping to find the exact mapping that defines this thing.
That's how it relates to the genetics.
This is how it kind of relates to the genetics, exactly. And Neil, I feel like I'm still not answering your question over here, but the idea is that this was linear. We started with linear. All of a sudden, I've got nonlinear. So piecewise functions are even though they have linear segments, they're nonlinear. I've got nonlinear. I'm getting an output. I feed these inputs and I'm getting a nonlinear output of these 4 inputs over here. I'm getting a different nonlinear output of these 4 inputs over here. I'm getting a different nonlinear output. And then if I pass these through another layer, I'm getting really just like multiple crazy nonlinear outputs associated with these things. Yes. So the question is, do we have a different activation function on each node? Typically, inside of the network itself, you have one type of activation function. either linear or ReLU or leaky ReLU. So the network, the activation functions inside of this network tend to be like one of the on the linear side, because you can sort of imagine that the sigmoid becomes computationally prohibitive. It like doing all of those sigmoids hundreds and hundreds of times was actually the thing that held neural networks back. Like it drove them forward, but they were so computationally expensive that like they were kind of limited. And when people realized that, oh, actually, like if we have the right linear function inside of here, these things can explode with complexity because we're not spending all of our time doing sigmoid functions. Like that's, but at the end, we do kind of need to squash these back down into a dimension of like categorization. So we have a different output function in the end than the input function. Anish.
How do you know how many like square things you need? How do you know how many like?
Yeah. How do we know how many we need? So let's take a look at it. That really is the ultimate question right over here, right? So let's say if I just have two inputs, and I want to approximate these things, and they're going to map very nicely to, or even just like a single input. No, two, I guess makes sense. If I want them to map to something like basically trivially like linear over here, like I don't know, like the points are above a simple linear function versus not above, is like the data isn't messily connected. I would have a few number of layers over here. So there are two things that we can add to this. We can add width and we can add depth. And by width and depth, I mean two different things. And I actually have this described in the presentation over here. So I'm gonna take a look at this. This is way over here. So we can add width. Adding width means adding along this sort of dimension heading out this way, right? Adding more layers over here. Adding depth means adding out in this direction. So this is my depth direction. This is my width direction. Thank you. This is my width direction. Thanks. So the reason to add width for it is that you can learn complex functions. So if we think of adding width and kind of going out further and further and further with this thing. So if I've got maybe very narrow network, right? Maybe only two inputs over here. And if I have I1 and I2, these guys are going to be connected to every single one of these ones, right? So everything's going to be fully connected to all of this stuff. I'm going to have a dense network where each of these lines represents some weight. If you can think of the output that we would have over here as the superposition of all of these complex nonlinear functions, what I might actually get is something that runs, that maps input, whatever that input function is, and it just kind of like goes up and down. It's like almost like you can make the I don't know, I made a wampum belt over here. So you can effectively make a highly nonlinear function by creating the superposition of all of these individual nonlinear functions. Yes.
Like each node is getting the same.
If each node is getting the same inputs, I didn't quite hear that. So each node is getting the same inputs, but it's outputting a different output. That's a great question. Each of these lines that connects the input to the output has their own weight. So every single connection between input over here, this guy has his weight. This input to that output has that weight. This input to the third output has a different weight. This to this guy has a different weight. So all of these inputs times however many outputs I have is however many weights that I'm going to actually have associated with these things. And so they're going to all be initialized randomly So the reality is that because the weight of this guy is going to drive some slope of this like ramp function, right? And the bias, so each of these nodes is going to have their own bias as well. So the weight of each node is going to drive the slope of the output of this piecewise nonlinear thing. The bias of him is going to adjust the shift of that mapping. The weight of this guy is going to do a different one. The bias is going to adjust the shift. So they're each little segment. I don't know if you guys are you familiar with like Taylor series expansions? Did you guys do that? When you think of like this one plus that one plus this one plus that one, when you start adding enough of these functions together, you can get some really complex output functions. And that's effectively that complex output function is what we're getting over here. I just needed to speak your language. I just needed to say Taylor series, and everybody's like, oh, yeah. Okay. I don't know if that helps a little bit. So the weight of each of these things adjusts the complexity of that. Yes.
So, when we're doing like that, like when we're doing at an individual neuron,
Mm-hmm.
we have like,
Yes.
you take those, you add them together, and then do you bias, and that's what causes that output graphs looking different.
That is what will cause this individual component of this whole like massive functional. Yes, that's going to be the thing that sort of drives it differently. Yes.
Can you explain what you were talking about before with superposition?
Yeah, so when I'm thinking like the Taylor series expansion, right, that's like this component plus this component plus this component. That's superposition. I mean, like the big sum of all of these individual functions. So the sum of all of these individual components becomes something highly complex in the same way that adding lots of like, I don't know, like x cubed plus x to the fourth or whatever like that can create something that like approximates a cosine that just kind of, the more we're just adding x squareds and we're getting something that becomes periodic ad infinitum. So the superposition becomes the addition of these, kind of small and not really complex functions. But the more of them that I add to each other, and when I add this already complex to another already complex thing, I am starting to get like orders of magnitude more complex out of this. That's the kind of like, I guess, big idea of it. These are great questions. I'm sorry, this is the first time I've gone through this with students, so I appreciate you bearing with me, but if we can all try to arrive on the same page with this, I really appreciate it. More questions? Yes.
For the second there, the weights change based on.
Yeah, so what we need to do is when we're actually like training this guy, I put it in air quotes, but when I'm actually training this guy, what we're going to do is we're going to go through and adjust everything. We're going to need to adjust all of the weights, right? So we evaluate a set of inputs that produces an output, and I take another set of inputs, and I kind of keep the weights set for a little bit to kind of see what that overall output is going to be like. I make an adjustment. The first time you make an adjustment, you see which way it shifted. And then we need to, it becomes a gradient differential. This becomes calculus pretty quickly. Like we sort of examine how these individual components are contributing to that overall shift. And if you evaluate the magnitude of the overall shift as it weights into that final output, eventually we're going to start saying, okay, which sort of shifts are responsible for driving this in the direction of like the right answer, and it becomes kind of like the genetic output thing. Yes.
So when we start counting the weights, are we shifting the weights for like all the nodes at once, or are we shifting in each node?
So yeah, so we're gonna start shifting everybody all together. So we're gonna like there's just like computationally we need to keep track of what the weights are gonna be and the relative shifts for each thing, right? So we need to keep track of all of the weights, how much they're changing, and how much the output is actually changing. That's the key over here, is making these things. And when we keep track of all of that stuff and we follow that path that is driving the output towards the expected output, that's our win. Yes.
So for the bias, is it applied to that, that weighted sum before you put it into the activation function?
Yes, the bias is applied before the activation function. The bias is applied before the activation function. So you sum up all of the weights, you add the bias, you take the activation function, and then whatever the output of that is becomes like the value that is going to go into here. And then these guys are going to have all of their values that will get fed forward from this one to that one and to this one. Yes.
So I was wondering, like, so when we have this like activation function.
Mm-hmm. Yeah, absolutely. So if all of the inputs are positive, and if I have some ramp function or some linear, like some ReLU function over here that's 0 below 0 and that, yeah, absolutely. If I have negative weights applied to all positive inputs, that's going to drive this function that's going to drive like a positive seeming function to all of a sudden seem like negative over here. And the bias of this function, so the bias of that function is going to be something that winds up shifting it left and right off of that y-axis. Yes, Kevin. So this is not this is kind of sort of what the percentile is like. So the percentile, we can tend to think of this as being at the last error or the last output over here. So but yes, in the sense that if this last output, if this final output, no matter what was sort of sitting before here, if this last output, here's my axes, and he kind of transitions. He's like less than 0.5 for below 0 and above 0.5 above 0. This thing shifts. I can sort of shift where that percentile is but like adding biases to the sum that preceded this transformation. Adding biases to the sum that preceded this transformation kind of shifts where that 50th percentile is. Yes. I don't know if that helps. Yes, more question.
So I see how bias would shift the graph like left or right. Do we ever shift it vertically?
Okay, do we ever shift it vertically is the question. The way to shift this thing vertically would effectively be to so you can build up steepness over here. We don't really shift it vertically, no. But what you can do is if I add some function like this, and if I add another sort of function that maybe cancels out the slope. So if I can create this effect of a vertical shift through the addition of a graph that looks like this and a graph that looks like that, right? So by adding these two piecewise nonlinear functions, the negative slope of this guy is effectively canceling out the positive slope of this output over here to create a vertical shift in the data. Yes.
Yeah, this might be like on or off track, but is there a difference between changing the bias and changing the weights of the points that are the output, like the points?
Yeah, so there is a difference between changing the bias and changing the weight. Yes. So changing the weight is changing how much we're going to scale each of the inputs that get fed into it. And changing the bias is also, it gets summed into the same thing. So, in a sense, functionally, no, I guess there isn't that much of a difference, but it does. I guess I'm just talking about like macro effects of what that is, but it all gets added to the same pot. The thing is, because it's independent, we kind of have like an mx plus b thing going on over here. So by changing m, we are definitely going to be changing the slope of all of those inputs Yes, absolutely. We're changing the slope of everything. But changing the bias value doesn't change the slope that's applied, doesn't change the scaling to any of the inputs that are applied to it. Yes, absolutely. Love it. More questions. More questions. I feel like this is really, really productive. Yes, Rohan. Yeah. So the question is, would you ever change the activation function mid-training? Generally speaking, no. We choose ahead of time how much width we're going to add, or sorry, which activation function we're going to add. We're going to use for this. And through whatever years of experimentation kind of thing, they tend to be the right answer tends to be these like leaky ReLU functions that are a very minimum slope below zero, and then they are y equals x above zero. And they so they're not completely undefined below zero. And intuitively, you can sort of imagine if we had a value that's undefined below zero, or sorry, that's zero. So for my activation that I keep talking about over here, this ReLU function, right? So if it's zero over here, and then it becomes x above zero, this is something similar to what we experienced in our genetic algorithms, is that if I start changing values around and there's no change in output, it's impossible to, like, if I still am projecting into this negative zone, little tweaks are going to cause no change in output. So I have no idea what I'm actually doing. I have no idea what my effect is having. So it's kind of like a dead node. It feels like a dead node over here. Like I have something that's not contributing. And even though we might actually be beneficial, I can't predict what's going on. So they kind of discovered that this leaky, that this ReLU is kind of a bad function, but the leaky ReLU function, which gives it an ever so slight negative slope, like a slope of 0.01, does allow you to basically differentiate this at values below zero, where you can make adjustments. You can see the impact that your change actually has. And we use these types of functions because they are computationally cheap. Sigmoids are expensive. 1 over e to the whatever, my God. You can do that in lookup tables, but still you're doing divisions, you're doing powers, you're doing stuff. That's a long equation. Mapping, decision below zero, yeah, that's yes.
So sometimes the genetic algorithms might be the same, you could just reset them.
Yes.
So is it gonna be, is that?
Right. So the question, so sometimes in genetic algorithms, it's the same, you just kind of reset everything. What you could have is that you could have it so that your weights don't actually find the solution that you have over here. Maybe as part of a training, we'll completely reset the solution. But generally speaking, we're going to try to design these networks in such a way that we don't have to do that. The odds of that happening are infrequent. Yes, for sure. Great stuff. More thoughts, more questions over here. So what we have been tasked with NN1 is to create a Python representation of this. Okay, what you're going to be tasked with is creating a Python representation of this. So you're going to be given a specification for a transfer function, an activation function, as I'm calling them. You're going to be given the inputs, and you're going to be given the weights that have already been trained. So there's no expectation of training. You're going to be given the weights that have already been trained that will generate output for these things. And what you're going to be expected to do is produce some output of this network. So basically, you're going to get something that looks like this. So let me go off of here. You're going to get something that looks, your inputs are going to be some weight file. So here we go. So I kind of printed this out, but it's going to be like some weight file, some transfer function, and some input. Okay. Now I've parsed the arguments So this is looking a little bit different right here, but the actual way it might be called is something like this. You call Python your file name, or sorry, your file name, the wait file name, your transfer function, and then you have your inputs over here. Okay. Thoughts and feelings on this one? How many inputs does this have? 2. Thank you. Yes. Okay. So I've got 2 inputs. I've got some wait file that we can worry about in a moment. And I've got activation function T2. What does activation function T2 mean? Activation T2 means he's going to give you 4 different transfer functions. Transfer function 1 is just X, the activation function, and this is going to be applied to all of the nodes in the network. So the activation function would just be X. Whatever it comes in is whatever you output. The second one is the ramp, which I've been calling ReLU over here, which is to say that it's X is equal to 0 for all values less than 0, and it is equal to X for all X greater than 0. Okay? So if I see T1, every single one of my nodes is going to have that linear function. If I see T2, each of these guys is going to have this. Every single node in this network is going to have this ramp activation function. This is logistic function, which I've been referring to as sigmoid. Logistic 1 over 1 plus e to the negative x. Okay? So, and then finally, twice logistic minus 1, so 2 sigmoid minus 1, which is what I'm calling tan h. It's the hyperbolic tangent function. It's the same function as sigmoid. It just maps from -1 to 1. All right, so those are your 4 activation functions that we're going to get over here. So the wait file is where it's going to get really weird. Right? So we're looking at this and I'm saying, okay, hey, this is straightforward, right? It's going to run this 522.txt. That'll be my wait file. Activation T3. Do we remember what T3 was? Sigmoid. Oh my God, cooking with gas. And then I've got how many inputs to this function over here? 1, 2, 3, 4, 5. Okay, so you need to keep track of the number of inputs, okay? Score. Let's talk about what these files are going to actually look like. So I put this is not going to be actual content from the file. Down here, this other stuff, your file will either be 1 or 2 or 3 or 4 lines long. These first 2 lines are what this file is going to actually look like over here. So within the file, he does something a little bit weird. These are not weights. These are final scalings that are done to outputs. I think it's just to guarantee that there's sort of like uniqueness of runs, that you're not hard coding, that you're like not hard coding something out. Like it's a test. So basically though, what we can do is that we're going to have to read the file, and the number of layers of this network is going to be the number of lines in the file minus 1. So this file right here is going to have 1 layer to it. Okay. This file over here also has 1 layer to it. This file right here has 1 layer to it. Sure, this guy has 1 layer. Let's see if I have a multiple layer. Okay, this guy has 4 layers to it. Okay, so this is a 4-layered neural network. And so for NN1, you're going to be expected to do any number of these things. And you can see I printed out the outputs of some of these files over here. This one is really long. I have no idea how many this is. I haven't looked through it just yet, but you could have lots of this, could have like 10 layers or something like that, right? So, and you're going to have to generalize and figure out how many layers you have by reading in this, opening your file. You've done this before, right? We did this with so many other things with our dictionaries. We're going to open the file. We're going to split it on new lines. We're going to count these number of lines. And we're going to say, however many lines, and sorry, disregard this, right? So that's for my own purposes. This is actually going to be what the file looks like. And so how many layers does this guy have? 4. Thank you. Okay. He's going to have 1, 2, 3, 4, 5 inputs. 1, 2, 3, 4 layers. And the final question is, how many outputs is it going to have? What do you think? 3. The last layer is the number of outputs, 3. So I've got 3 outputs. Okay, and this is post-network scaling. Post-network scaling. I don't know why there we have post-network scaling, but there's post-network scaling in the last time. My suspicion is that so you can easily check and see that I have 3 outputs, and each of these 3 outputs are going to be scaled by this number over here. Anish. There are no biases in these things. You don't actually have to implement biases just yet. Okay. The good news is we're not doing biases. So we're not like actually doing the neural networks right now. We have a fuzzy sense of what these things are doing, right? And I don't care if you're 100% on what they're doing, but you can at least maybe see that there are inputs that are getting scaled and biased. We're going to assume the bias is 0 for all of these guys. They're getting scaled, they're getting past activation functions, and then they're producing some outputs. That's the learning goal for before spring break. So conceptually, you're ahead of where we're going to be implementation. Okay. So yes. So what you're trying to get is a Python representation of a neural network. The objective of this is strictly, can you like write the neuron class that's going to sit at the core of this thing? Because we need to get the structure of these things. You need to be able to write these structures at scale so that when we say, hey, make 200 neurons in layer 1, make 150 in layer 2, like 200 in layer 3, that you have a built-in piece that you can construct these things to parametry. That is the goal. Okay. So the goal is, can you write this neuron class and can you compose them? And there's a little, I think it's slightly tricky the way this is described inside of here. And that's why I can see myself beginning to wean myself off of the autogrid. I have my problems with this as well. That's not to say that this isn't an entirely important and valid problem. Okay. So great. The next thing. Each layer is talking about weights. So if we look at this first layer over here in this file, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 numbers. Okay. I have 10 weights. How many inputs did I have down here? Do you remember how many inputs I had? 5. 5 inputs, 10 weights. What is that? What do you think that this is telling me about the next layer, the first layer, Anish? There are 2 neurons in here. So the problem is saying, can you figure out how many neurons are in each of these successive layers? And what are the weights to these layers? It's a cryptic way of describing this, okay? It's a cryptic description. So what I have, and I will make this over here. Let's do this. I can just do this right here. So what we've got are 5 inputs to neuron 1, neuron 2, I1, I2, I3, I4, I5. And the way that these neurons are going to be presented are that the first 5 numbers in the file are the weights to this first neuron, and the second 5 inputs in the line are the weights to this guy. Yeah. Okay. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the only way I was able to really figure this thing out was I said, I counted however many input arguments there were. I counted however many lines there were in this file. I then am going to treat each of these guys as a layer. So I've got 10 inputs over here, which means I have 2. So in my next layer, this is the challenge for you. I can draw this out. 2, 3, 4, 5, 6. How many neurons are in the next layer? Thank you. 3. Okay. It seems maybe obvious because I'm spelling it out in front of you, but it is going to be far less obvious when you are working your way through this. Okay. So looking at these 6, I had no idea. I could not look at this 6 independently. I needed to figure out row 1 first, knowing that this guy had 10. 10 divided by 5 meant this one had 2. Let's do this. So I had 2. This one had 6. Therefore, it had 1, 2, 3. 1, 2, 3, 4, 5, 6. How many in this? Thank you. 2. 1, 2, 3, 4, 5, 6. The final output is 3. And this last row is post-scaling, post-activation, final function scaling of by this amount for like error checking, basically for you to see, yes, you should have 3 outputs over here. We're just going to scale these for whatever. Okay. Would you like to do another example? Okay, I can do it. Here we go. Ooh, this is a little bit, look at this. Okay, here we go. So the file, just to be clear, is going to look like this. This is what the file is going to be, right? It's not going to have this extra stuff down underneath, but you're going to be called like this. T4. You're going to load the file. T4. What is T4 meaning? What is T4 referring to? Yes.
Times.
2 times sigmoid minus 1. Tan H function. It's a sigmoid that's scaled and offset so that it maps between -1 and 1. So your final output is -1 and 1. Sometimes we don't like to do the classifications of zeros and ones. Sometimes the classifications become -1, +1. That's an alternate, like very normal use and representation of neural networks. So that's where this tan H comes in. Okay. How many inputs am I looking at over here? I've got 1, 2, 3, 4, 5 inputs. Okay. Maybe a little bit hard to see. So what I'm going to do is I'm going to do a Control F on a space right here. So how many layers are going to be in this network file? Thank you. 2. How many outputs in this network file? 2. Thank you. How many nodes in the first layer? 2. Thank you. How did we get 2? Okay, how did you get 2? There's 10 divided by the 5 inputs, 2. Excellent. How many nodes in the second layer? 2. Right. So I had 4. I had 4 weights. This layer had 2, therefore this layer has 2, and I have 2 outputs, and this is post-scaling that is applied to these 2 outputs that's going on over here. The one that my code gets wrong is actually this one. My code is getting this one wrong because I'm doing something stupid. But this is going to be your like first problem over here. How many inputs? 1 input. How many nodes? 1. Post-scaling 1. T1 ramp function. Okay. So I have 1 node, 1 layer. The input layer is also the output layer. And that's where my code is not happy because it didn't like that the input layer. This is not like something you would normally find in neural networks. Okay, a lot of the problems are going to look like this though. 2 inputs, 1, 2, 3, 4, 5, 6, 7, 8 over here. So I've got 8. So that means the first row has 4. Okay. And the first row, I only have one layer to this thing because the file is only 2 lines long. So 2 lines long means that I've got one layer. And I can count this, or I could do my division, and I would see that I have 4 outputs over here. And the weights of each of these guys to be explicit of these things, right? So if I have I1, I2, I3, I4, the weights of I1 so we said there are 2, the weight of I1 as it weights into here is going to be 0.5. I2 is going to be 0. I3 is going to be 0. I4 is going to be 3, right? So this is 3. So we're going right side first, right? So I went through, I did down the thing. So I went 1, 2, 3, 4, and then these are going to be my weights that go down to this one. So the weight of that one goes into here is negative 0.25, and then 0, 0, and then finally minus 2. I've got some nods. Do you want me to repeat that with a different example? Okay. So I can take a look at this guy. I have 3 inputs, right? So I have a ramp function. I've got 3 inputs over here. I have 1, 2, 3, 4, 5, 6, which means I have 2 nodes. Thank you. I've got 2 nodes of this guy. I've got 3 inputs, I1, I2, I3. I figured that out from these guys. The first weight of I1 is 0. One. Negative 1. Yep. Yep. That's it. So you're going to take, so let me just finish this example out over here. So we can say this becomes a 1. This one becomes the negative 0.5. And this guy becomes the 1 over here. So what are we outputting? So because this is a T1, I'm going to weight input 1 times 0. So it's I1 W1 plus input 2 times W2 plus I3 W3. So I weight each of these inputs. I do the multiplication. I add my bias, which is going to be 0 for right now, but I think it's a good practice to have the bias inside of here, plus my 0 bias. I take all of that stuff and I apply my activation function, and that becomes his output. Okay? For this guy, I'm going to weight my input times weight plus input 2, weight 2 for this guy, input 3, weight 3 for this guy, plus my bias, in this case is 0, and I apply my activation function to that collective sum that we have over here. I have 2 giant sums that come out of this thing, and they get then scaled by 2 and then 1, just for like bookkeeping. Yes. Yeah, the activation function needs to be in the neuron class. I agree. Or at least the neuron needs to know which activation function it's using. I'll put it that way. This is recorded, so you can at least look at this. I feel like I've spoken for an hour, but I feel like this is like more interactive than. So watch it on double speed. All right, next, let's talk about how to actually do this. So for my 4 demo, I'm quite happy to give you this. Right, like this is not the hard part. So I don't really use random. This is the deal. So weights I'm going to open my args of 0. I'm going to read it. I'm going to split lines, and then I took the wave file name. I just do a pop 0. Have you guys started doing pop 0 on the args? If you haven't, it's kind of nice. It's a nice thing to do. What does pop 0 do? Remind me what pop 0 does. Yes.
Just kind of removes the first item and stores it in the variable it's assigned to.
Exactly. So I can pop 0. If I pop 0 off of this guy, all of a sudden he's gone. And then for my activation function, if I hit pop 0 off of that guy, he's gone. And what am I left with? The inputs. So popping 0 your way through args is actually a nice way to get left with only the stuff that you care about. Okay, so my general approach to these problems, and I realize I probably should have said this, so this is not included in args. I got this guy. I don't really care about what the file name here is, right? But if I pop 0 off of this args, boom, gone. I pop 0 off of this guy, boom. Now args is equal to this guy, and I can just treat this as args, and I can parse, and I can do whatever I need to do with my args over there. So definitely work through popping 0 on your args. It's to your benefit. Okay. So that was this guy. I should second order of business. Oh, yes. Sure. Third. So here's my ramp function. The activation in this case is actually pretty straightforward, right? Like the ramp function, that I feel like there are no secrets given away over here. That's actually the activation for these things. And the simplicity of this function, or the simplicity of this function right here, of this ReLU, is one of the reasons why it's chosen as a component of these networks. That is far less complex than the math of the sigma, right? And if it can just use this function in combination and like tailor kind of some feeling of these things, and to create nonlinear functions, well, that's geez, that's great. Yes, Kevin. So you are not really given choice. This lab is saying make this network the way you see it, the way it is, and you're evaluated based off of whether or not you produce the output. So it's checking for like the numerical feed forward. Can you construct this network? Can you take input arguments? Can you feed them in and scale them and weight them appropriately to produce the actual output? So we're not worrying about like design choices for fitting. We're not worrying about design choices for like width and depth. All of that stuff is getting. And I appreciate that you guys have been asking these questions about how do we find this? What is the point of what? Because that's where I plan on going. Like that's kind of the goal for this. So I guess I'm deliberately giving a top level treatment of this. But your brains are all over here, which is great, which is my goal. Okay. I don't know if that answers your question. So this isn't like choosing. This is more just doing. Okay. So sure. Here we go. This is something though that I want you to take a look at. Activations. What are min and max in Python? You used it? Yes. Okay, let's put it this way. What kind of data types are they? What is that a variable? Is min a variable? Argument, it's a function. So what I've done over here is I've made a dictionary that's keyed, but the values are functions. So I'm sorry, I realized I asked the wrong question. The value is a function. So if I say activations of activation function over here, what I'm really doing is I'm choosing to run a function based. I'm calling by accessing a key value from, or sorry, a value off of the key value pair in this dictionary, I'm actually retrieving a function, and I'm using this dictionary value to run an actual function over here. So let's do this. Let's say us here. I'm going to run into here. What did I call this? I called this NN3. Python NN3. And if I say something like A1 over here, right? W244, it's properly argument parsing. Okay, so I've got my A1, right? By saying A1 as an argument, I'm teasing out the argument. Let me do this, CLS. What I'm going to run over here is I'm giving this an argument of A1. A1 is being passed through, and I'm grabbing it as an activation function. And then I'm retrieving the key from A1, which is to say minimum, which is a function. And then I'm running this thing, which is functionally equivalent to saying min. Do we agree with that or disagree with that? Yes. Tell me yes. Yeah.
Text file, it was like.
Right. So this is a separate. This is a proxy for you saying T1 is the ramp function. So if I say I can pass function names, I can basically call functions through arguments. It's a built-in switch statement. You can use dictionaries as built-in functional switch statements in Python. So by saying T1, if I say T1 or T2, yeah, this is not the actual answer, but like, let's say, I don't know, set, right? So if I were to say my activation's T1, this is going to call the set function on this list over here. So if I were to run this over here and I say T1, I wind up getting a set out of this. So the point is that if you write your own function over here, you can use dictionaries as like case switch statements in a sense. I'm going to back off from that because I feel like that's not the most important thing. You can deal with that and whatever. That's not critical. That's just a shorthand. This is kind of the thing that I wanted you to be aware of. So what your file is probably going to need to look like, this is the scaffolding you're going to need. This is the pseudocode. You're probably going to need math. I think math.e is your friend for those of you who haven't used this yet, right? Math.e is your friend. TANH, that's my name over here. Class of a neuron. So for me, to get this thing to work, all I really needed to do was get two functions over here. And Python classes are defined with the words class, right? So I say class whatever. And we have this underscore underscore init function. So when you call the initializer, when you say neuron of something, it's going to call this init function with the argument. And I know that some of you guys haven't done Python classes over here, so this is where I'm saying I'm ad-libbing, right? So the first argument is going to be self in class functions within Python. The first argument is self. And inside of this class, just like any other Java class or whatever you might have had, we want to make sure that we have the appropriate elements that are going to be needed for this thing. The weights, you're going to need to initialize each of these guys with the weights. You're going to need to initialize each of them with some bias. At least for now, it's beneficial to have this. And they're each going to be need to initialize with an activation function. Ask me questions on this or feelings. on this. Yes, Josh.
So those weights, like the weights coming in from the previous layer.
The weights are going to be the weights defined by that file. The weights are going to be the weights defined by the file. Okay, so this is an important distinction. The weights are going to be the things that we adjust later on. The weights are the things that we twiddle. The weights are the things that, if we go back, with all those arrows that define that mapping from one to the other, the weights are these guys that are coming out of here. 0, 1, 1. So here, my neuron, so I had three inputs to this guy. So that meant that these are my three weights for the neuron that we had over here. So basically what I'm seeing is this neuron of whatever this is, like 0, 1, -1, right? I'm making this a neuron, and then I'm making another neuron in that same layer, neuron of 1, and this is going to be some list, -0.5, 1. And that is the layer that we've got inside of here. That is this layer right there. Yeah, I've got some nods. So, and we don't need to initialize with bias over here, but over here, like, let's take a look at this guy, right? So I've got 1, 2, 3, 4, 5 inputs. I've got 2 outputs. So I can effectively look at this as 1, 2, 3, 4, 5. If I've got this guy over here, I can see this thing as my layer is going to be a neuron of this 0.7, 0.6, 0.1, 0.5, 0.5. And then I'm going to have another neuron of this list. And realistically, these are probably going to be some slice of the input that came in over here. Yeah. So we're going to need to slice this layer apart, pass that slice or whatever that list to the neuron, and that's going to create your new neuron out of here. You don't need to say words like new. It's just, we can just pass that the argument. So you never actually put data in for this neuron. When the self, it's used as part of the class definition, but you don't actually feed it anything. And so, long story short. And so here I've got my activations over here. I use this basically as a case switch for like defining which activation function I'm going to use. And so what we're going to need to do, I kind of skirted over this, but you're going to need to take that Python data file. You're going to need to split those strings and make them into the floats. Yeah. So those strings are going to need to come in as floats for each row that's inside of there. You're going to need to figure out the number of outputs that you have. You're going to need to figure out the number of layers and the number of inputs that you have. You guys have all showed that, like, intuitively you're there, right? So we're not like guessing around. We know what that's going to look like. The tricks become, how do you figure out the layer sizes? And we already know that they're going to be they're going to be the length of the row divided by the number of inputs to that row. So we need to use the preceding row information to figure out the number of inputs in that row. It's not just by looking at that file. It's not just by looking at that row. It's by looking at that row and the preceding row going all the way back to the inputs. So we need to figure out that number. Then it comes time to make your network. So what we're going to do is we're going to make this network. I think this can be done just as making a list over here. And for each layer, so you're going to know how many layers that you have inside of here. You can make a network layer to be this neuron with initialization parameters for n and the number of neurons in that layer. Right? Like for each number of neuron, you're going to need to say, this is neuron, comma, this is neuron. And then we're going to make another list. And then I say append that network layer. This stuff down here, preceding size is this size. That could be helpful stuff. Wait, really? Yeah, this is helpful. This kind of was necessary. I needed to, but you can disregard this if you want. I was keeping track of the sizes of each layer, and basically I was saying the size of this layer is then the preceding size so that I could always just kind of look back on it and say whatever the preceding size. It requires initialization. Then that actually becomes like on the thing, right? So after you've initialized all your neurons, what you're going to do, so now all of these neurons have been given initialization. You have got arrays of classes. You're going to generate the output by feeding it the input, and the input is going to be the output from the prior layer. The input is the output from the prior layer. The input is the output from the prior layer. The neurons themselves take care of the weights because you already did that. The neurons themselves take care of the activation functions because they already did that. The neurons themselves are going to take care of the biases because they're already configured to do that way. So that class is going to be fed some input. It's going to do the weighting. It's going to do the scaling. It's going to do the summing. It's going to do the activation function. So to be clear, what this thing is going to do, right? So your class over here is going to do the weighted sum of all of the inputs plus bias. It's going to really say, the activation function of the weighted sum of all these guys. So we're going to need to run that output method on every single neuron of the inputs. How do you feel about that? Tell me things, ask me questions. It's somewhat confusing, but I think that if you can draw this thing out, and I will give you, I'll post these files up onto the Schoology. Today's a little bit chaotic, but I will 100% have everything squared this away by tomorrow. If I don't get to it today, I have to do JDA basketball stuff during the day today, and then I have to get other stuff during the second block today. So, but I will make sure that these files are there for you to look at and to digest and to understand and to think about. Thoughts and feelings on this. Do something. Here is mine. So really, what we're kind of looking for, you can start with this, right? My class neuron over here. When I call neuron of something, right? So if you haven't done this, and I think I guess ad lib, sure, class dog. Yep. I will accept the AI description of this thing. You know, when you make the class over here, the initialization parameter is always going to be the same. You define the self, you define the parameters like you saw in your other classes. We can pass in some input arguments going on inside of here. And then this is going to be your actual. So we have our definition, and then we have our use methods over here. And so right now we just need the output. We just need to tell it to output. Later on, we're going to need to tell it to like adjust these inputs, return the biases, return the weights, apply this transform. We're going to need to adjust this thing. But for right now, we just need it to do that part. So here we go. You call the class, you make an instance of the class by calling the name of the class and calling this guy. So you don't actually invoke that init function explicitly. For my Python people who are new to making Python classes, we're not going to do that explicitly. What you're going to do is call the name of the class with the arguments, and then absolutely we can access these things. So I've got my class neuron. I'm going to define all these things over here. Okay. Anything else that you want me to revisit in the final 10 minutes? I've spoken for like literally 90 minutes today. This is horrible. No, stunned silence. Do you want to just take 10 minutes of stunned silence then? Finish out. Okay. Sounds good. That sounds like a delightful way to spend our time together. I'm going to stop this recording.